Hi folks, it's Alan here. This one's going to be a slightly longer format video. I was going to talk a little bit about what it takes to bring this incredibly decrepit Pink Triangle DaCapo D2A converter back to life again. Now, you may remember that this particular model that I've been working on here for quite some time, actually I got it spares a repair, but boy did it need a lot of repair. Let me just show you what it is we're talking about here. So when I got this particular D2A converter, I have to say it was in a pretty sorry state. So I've had to do a huge amount of work on this in order to bring it back to life. First thing is the actual power supply module that was supplied with this one was extremely dead. I still have the original power supply here somewhere. And you can actually see that one of the two transformers here is pretty much burned out. Now, the reason why that power supply module had burned out was actually down to these things. It's the capacitors, the smoothing reservoir capacitors on the main PCB. Pink Triangles are rather notorious for this, but the capacitors had all basically, the electrolyte had leaked out. And actually you can see it's done a bit of damage here to the printed circuit tracks. It's not the end of the world and I've managed to repair everything that needed repairing. But nevertheless, that was a bit of a problem. So all of these capacitors here had to be replaced. Actually, it was slightly worse than that. Underneath these capacitors, the leakage had actually got underneath some of these slightly smaller capacitors, the tantalum bead ones, and actually it even got underneath some of these LM337 and LM317 regulator ICs. So there's an awful lot had to be replaced in the power supply stage to this particular DAC. Similar problems over on the 5-volt stage, although actually it looked like somebody had already had a go at repairing this. They've replaced the original bridge rectifier with another bridge rectifier in this, so it looks like that one's also had problems in the past, but somebody else had fixed that. But even once I'd made all of these changes and modifications, sadly, I still had absolutely no joy, and it turned out it was down to this thing. It was the D2A converter module in the middle. Now, Pink Triangle D2A converter modules are a really interesting beast, and I'll talk a bit more about how they work in a minute. But sadly, this one was potted, so it was extremely difficult to kind of unpick what was going on behind the scenes. But I managed to get another D2A converter, and I did actually find it out. Now, the thing that's really interesting with this is actually what this module's doing. Clearly, this is one I've replaced, and basically this is my new module that's working absolutely fine on this one. But actually what it does is quite interesting. Now the filter module, which is this thing here, this one's got the lid off so we can see what's going on inside here a little bit, but the output from the filter module is basically a single bit stream. Effectively it's a bit like pulse width modulation, only slightly different. It's a 1 means send the output voltage up a bit, a 0 means send it down a bit, and by sending out 1s and 0s at the right kind of frequency, you can convert that into a reasonably accurate digital to analog output stage, and you can effectively convert that just with the analog filter, this lot here, back into an analog voltage, and it's a pretty good DAC. In fact, this chip in here is actually a DAC in its own right, and actually just by feeding the output of that straight into this analog filter stage here would actually produce a halfway passable D2A converter. But Pink Triangle went a lot further, and this is really the secret in this module of actually why the Pink Triangle DaCapo DAC was quite so good. And it's down to the attention to detail that's gone into this, and there's a lot of stuff that we need to talk about in here. First thing is this stage here, which I have to say is probably the one that I found most challenging of all. Coming in via that green wire there is a clock signal, with the left and right input channels coming in via the orange and the yellow wires. And the first thing that they do in this is they regenerate the clock signal and effectively regenerate it. It starts off as roughly a 16.9 megahertz clock signal, and coming out of these two ICs on the right hand side here is actually another 16.9 megahertz clock signal. But the green one has got jitter in it. It's not necessarily perfect. It's also used for quite a lot of other circuitry which introduces noise. However, here we've got two phase lock loops, and the phase lock loops basically lock on to that input signal and output an absolutely clean, absolutely precise, totally jitter-free 16.9 megahertz clock signal. Now, I have to say, this was probably the biggest nightmare trying to get this tuned, because these phase lock loop ICs, 74HC4046 ICs, they're sort of a bit analog. So the first couple of ICs I tried just simply wouldn't go high enough in frequency. They only went up to about 14 megahertz. The next couple were just too jittery. They just wouldn't lock on properly. The next ones after that, actually, I managed to get them to lock on. But you can see in this one, I've actually got a whole stack of little components on stands there. And this is because even the datasheet for these things says we strongly recommend experimenting to try to work out what the best component values are. So that's exactly what I had to do, and it took me quite a long time to get that right. And I have to say I'm pretty pleased with that now. You can also tune the locking using the potentiometer here to make sure that it really does lock on well. But okay, so why do we do that? Well, actually, it's about what happens in this next stage, and this is just left and right channels duplicated. But actually, the first two ICs here are simply used to take that clock signal and re-clock the digital data stream. So the data that's coming in via that yellow wire there goes into these two chips here, is clocked using the clock signal generated by those phase lock loops. And what should be coming out of that is an absolutely precise, very, very accurately clocked signal of ones and noughts. But even then, that's not quite all. What they've then done is they pass that through another couple of gates and basically reclock it further within the gates. But more importantly, they then phase correct so that you've got both a positive and negative signal. And you see this little capacitor down here at the bottom. That little capacitor down there is just used to correct the phase and correct for the latency within different chips to make sure that the signals that reach this really important output chip here are absolutely precise, and there's one positive going signal and one negative going signal. Hence there are two wires, the grey wire and the red wire, going to each channel, and the purple and the blue for the other channel. The final chip on here is actually just a hex inverter chip, but all three channels are paralleled up, so three of them go to the negative end, which is the grey wire, and three of them go to the positive end, which is the white wire. Now what I've done here to really make sure this is even better than the original D to A converter, of course the original had power supply modules that went into it from the analog side of the circuitry, because in fact the voltage output by this logic chip here is critical to the final output voltage. But I've gone one stage further than that, and I've broken the power supply down yet further. So in my module you can just about see U5 is a 5 volt very low noise regulator that's used to power the first four chips in this circuit, and U2 is another regulator that's just used to power that 74AC04 chip that's on the left hand side there, and that's basically means that you do get absolutely precise voltages as well as absolutely precise timing coming out of this thing. Net effect, once that then passes into the analog filter stage here, pass it through second order and fourth order filters, various other bits and pieces, go through a couple of op amps and feed the output signal into there, and well, the net effect is this thing sounds absolutely cracking. I'm really, really pleased that I've managed to bring it back to life. I'm really pleased that it took quite this long to actually decode what the heck was going on in this Pink Triangle, and it's also brought out a whole load of ideas about things that I could do with more modern components that I might be able to use to further improve this design as time goes on. Looking forward to seeing what happens next. Thank you very much for listening. Hopefully I haven't confused you too much, because I certainly confused me while doing this.